So we're going to start by looking at 5.4 part 2. Okay, still on logarithmic functions. I'm going to start with a problem that involves using properties of exponents to rewrite something. So we've seen when we talk about logarithms, a lot of times exponents are tied in with logarithms, and some of the rules of exponents come up. So I just want to go over what those rules are using this problem. So I want to rewrite this, but I want to rewrite it in terms of a to the x, a to the y, and a to the z. So to do that, we've got to look at that exponent and look at the different operations that are happening and think, why would that have happened? What would have caused you to add two things together in an exponent? What would have caused you to subtract in an exponent? Okay, there's a rule for that. So let's start with the addition. What would have to happen, like think of a problem, that would result in adding exponents together? When would you add exponents together? Yeah?
I just based on multiplication.
Can you give me an example with like numbers?
2 squared plus 2 cubed.
And what are you doing?
Times 2 cubed, sorry.
Yeah. So whenever you have the same base and you're multiplying, you can add the exponents together, and that would be 2 to the 5th. So let's apply that same idea here. What would I have had originally if I have a to the 2x plus 3y? Just start with that.
A to the 2x times a to the 3y.
A to the 2x times a to the 3y. Now minus z. What would cause me to have to subtract something? Right, if I had division, then what would I be dividing by? A to the z. Okay, so now we've got one part of it. We've got the a to the z. Now I want to make sure I have a to the x's and a to the y's. I don't want a to the 2x. So now think about that operation. 2x. What operation is that? That's multiplication. What would cause you to multiply two things together and put the result in an exponent? Yep.
Power.
When you have a power to a power. So can you tell me what this might have been originally?
A squared to the power of x.
You could say a squared to the power of x, or what else could you say?
A to the power of x squared.
Yeah. So I'm going to say it like that just because they specifically said to write it in terms of a to the x. Okay, I've done that. A to the x squared times, how about a to the 3y? A to the y, that's what they wanted me to have, cubed, over a to the z. And that's it. So we just rewrote that expression in terms of the three things they want. A to the x's, a to the y's, and a to the z's. Any questions on that? So let's take a look at something. We've already done this before. In fact, we already did this exact problem. We had a problem probably back last week, maybe section 5.1, about a population of 50,000 people increasing at 2.5%. And the question was, how long would it take the population to double? So first thing we have to remember is our equation for exponential growth or decay. So we'll figure out which one this is. And then we'll plug some numbers in, and we'll solve it first the way we've done it before. And then I'm going to show you how to solve it algebraically. Okay. First of all, is this an exponential growth problem or exponential decay?
Growth.
Right. It's growth because we're talking about something increasing at a percent rate. Any anything that increases at a percentage is growth.
Wait, alright, even if it says like it's increasing by 0.5% each year, would that be growth, or would that just be written incorrectly?
No, you could increase at 0.5%.
Okay.
That's a smaller increase. If you said decrease at 0.5%, then that would be decay.
Oh, yeah.
But an increase of 0.5 is still an increase, it's just smaller.
I thought since it was less than 1, it'd be subtracting the overall total.
No, it's still increasing. Even if it says you're increasing at 0.0001%, it's still growth. It's just extremely slow. Okay, so how long will it take for the population to hit 100,000? When we write exponential growth, does anybody remember what we start with? Wait a minute, yeah?
So like your original number?
Yeah, we start with the original amount, which in this case is how much? 50,000. And then there's something in parentheses with addition, yeah?
1 plus the rate?
Right, 1 plus the rate as a decimal. This is the percent. So what's 2.5%?
0.025.
Yep, 0.025. And I need one more thing. I need a t because my formula says I'm finding an amount as a function of time. Well, where's the t going to go?
As an exponent.
As an exponent. And that's the whole thing that makes this problem not an Algebra 1 problem. You have a variable in the exponent. But we just went over a rule in the first part of this section that allows you to move that exponent somewhere, depending on, well, there's a rule. We'll look at it. Okay, so there's your formula. And what are we doing with the 100,000? That's A of t. So this is going to go right here. We have 100,000 equals 50,000 times 1.025 to the t. And before we even graph it, we did something on both sides just to make the numbers smaller. You could divide by 5,000, but we could even do 50, yeah.
Yeah, that's what I'm saying.
So that's gone. And what's 100,000 divided by 50,000? 2. And algebraically, that is where we stopped last time. What did we do from this step to finish solving for t, yeah?
Plug one part of the equation on y1 and the other in y2.
Okay, so 1.025. How about window? What would be a good minimum for my time?
0.
0?
You didn't do it to them.
You didn't
Oh, I didn't
put
put the
the
exponent.
exponent.
We would have noticed that pretty quick. Okay, so good. That's a good minimum. A good maximum? Well, it's going up at 2.5%. So essentially what you're doing is if you start at 50,000, and let's say you went up 2.5% the first year, you'd multiply by 1.025. That's your population at the end of the first year. If you do it again, second year, third, fourth, fifth, sixth, seventh, eighth, 9. So you can keep going till you get to 100,000, and that'll give you an estimate. I mean, I'm already at 10, 11, 12, 13, 14.
I see, like,
So that's 20 years, and I'm getting pretty close.
so 40, 50.
So I don't think we have to keep guessing. We could just say, all right, it's probably around 50, maybe 40 years before we hit 100,000. Population doesn't, it's not going to go negative. But remember, we don't need to go all the way to 100,000 because we simplified it by dividing by 50,000. We only have to go to 2. So that's a lot lower. I just set it at 5. And if we didn't go far enough, we'd go a little further, but I think we're good. And what did we do from there? Find the intercept. Okay, I'm doing this because then when we do it algebraically, I can confirm we did it right. So it says it should take about 28.07 years. Okay, so that's graphic. We've done that. Let's see how we could finish solving this algebraically. So we've got a t up in the exponent. It'd be a lot easier if that t wasn't in the exponent. We are allowed to move that t, but you can only move it if you have what in your equation? Logs, and we don't have logs. Well, you can introduce logs. Just like you could introduce a square root to both sides of an equation, you could introduce squaring to both sides, you can introduce log to both sides. Just do it on both sides. So take the log of what's on the left, take the log of what's on the right. Now, what can I do with the t?
Just move it in.
Now I can move it to the front of where? Like all the way in the front?
No, in front of its own log.
In front of its own log, yeah. So log 2 equals t log 1.025. That's multiplication. And now how would I get t by itself?
Divide both sides. The log of 1.02.
Yeah. Divide both sides by log of 1.025. That cancels. And there you go. If we do that out, we should get 28.07 years. Let's try it. Log of 2, close parenthesis, divided by log 1.025. And we get exactly the same thing. So in some cases, it might be faster to finish it algebraically than it was to type it in Y1, type it in Y2, set the window, graph it, calculate the intercept. This is probably faster to type in. Any questions on how we solve? All right. Now let's go back to this for 1 second. Let's say I wanted to change that equation to log form. Not take the log of both sides, but change it to log form. That was the first thing we talked about in the last section. If you want to write something in log form, what's the first thing you have to write down?
Log.
Log. What is going to be my base? 1.025. Logarithm always equals what kind of number? Exponent. What was my exponent? T. And the thing that's by itself, that becomes my argument. So all I did there was I rewrote it. The problem with rewriting it this way to get the answer is up till now, we don't know how to take the log of base 1.025. But this, we figured it out, was that. Because that t is equal to log 2 divided by log 1.025. So that should give you an idea of how you can take a log where the base is any number you want. All you have to do is take the log of the argument and divide by the log of the base. So like if you wanted to figure out log base 3 of 8, all you'd have to do is log of 8 divided by because the 3 is in the bottom and it's lower, it goes lower over here. It goes in the bottom. And that's something we're going to talk about called the change of base formula. But it gives you a way to take a logarithm where the base is any number you want. I did not do the problem this way with you guys because we didn't know how to do it. But what I did is I basically proved how to take the log where the base is not a 10 or an 8. So if I was doing this problem at this point, I would not have done any of that because I know the change of base formula, and I would just type this in on my calculator to get the answer without change of base, without taking the log of both sides. Any question on how we got the 28.07? Okay. So sometimes what we do is when you have a set of data points, you try to find a line that models those points. And something like this. I might draw a line through it like that.
Like a scatter plot.
Yeah, like a scatter plot, you find a line that kind of models the direction of the points. Well, what I just drew there is called a line of fit. A line of fit is a line that you estimated that goes through the points pretty accurate. Now, let me show you something I can do on the calculator. Bless you. I'm going to make up some points that aren't quite in a straight line, but they're going to be close. Let's do 1, 1. Let's do 3, 2. Let's do 1 up here. Maybe 1 over here. And 1 more up here. All right, so they're pretty close to a straight line. Right, and I got 5. Now, if I want to fit a line to that data, I could try and estimate it myself. You know, maybe about like that. I got it going right through 2 points, and then I got 1 below, 1 above, 2 below. That's pretty good. Might be a little bit lower. But that's called a line of fit. Now, let me do something a little different. Let's take the calculator.
Just like a trend line of data points, though.
Yep. That's what a line of fit is.
Okay.
I'm going to put all these points in the calculator. This part you can watch because we're not going to be calculating a line of fit. We are going to calculate something, but it's not going to be a line that we do. Okay, let's put these in. So to do it, I go to Stat, I go to Edit. I think we did this once way early on. Put in all my x values. So I got 1. Looks like what? 3, 4, 6, and 7. Now I'm going to put in all my y's. 1. What's this one? 2. The one that's at 4 looks like 3. 1, 2, 3, 4. 6, 4, and then 6. 7, 6.
How do you? Oh, this is for the scatter plot.
Yeah, I'm just typing in those points I made up. Now, if I clear my y equals, and I do zoom 6, I don't see any of them. I don't see any of them because I didn't turn on the scatter plot. The data is there, but it's not turned on. So if I go to y equals and highlight plot 1, now the scatter plot is on. And if you want to see more about what is plot 1, you can press second y equals. And it'll show you all kinds of things about plot 1 if you hit enter. First of all, it tells you if it's on or off. It tells you what kind of plot it's going to be. You want to do a scatter plot, you want to do a line graph, you want to do a bar graph, do all kinds of
You can do a Fox and Whisker plot.
Yeah.
Graphic calculator.
Fox and Whisker plot. Yeah.
Wow.
And it says, well, there's lots of lists in the calculator. So which list is the x's coming from? L1. If you go back to stat and go to edit, you'll see that I put
Where's the?
my x's in L1.
You get the stack edit there.
And I put my y's in L2. But there's also an L3, an L4, an L5, an L6. There's a bunch of them. I always use L1 and L2. And I can change the color and all kinds of things. But I don't need to change anything. The only thing that I had to make sure that I do was turn the scatter plot on, which you can do from the screen, changing on to off, off to on, or you can do it right at the y equals screen. Now, if I hit graph, I will see the points that I just made. And what I can do is go to stat, and I can calculate not only a line of fit, but I can calculate the line of best fit. That means it's the most perfect line that would fit through those points. It's not an estimate. It's a calculation. And that's called a linear regression. We're going to do a type of regression today, but I'm just showing you the linear one first, and then I'll show you the one we're going to do. If I click linear regression, and I don't have to change anything, I just press calculate, it tells me in y equals mx plus b, or they use the letter a for the slope, what the slope should be and what the y-intercept should be for the most perfect line you can get through those data points.
Sorry, how do you get the line over here?
It's under calculate.
Okay. Alright, and how do you edit the
We're gonna go through and do it.
points? Okay.
Yeah. So that's a line of fit. If you take statistics next year, you may learn how to do this. How do you calculate the best slope and the best y-intercept you should have for a set of linear data? And there's a process to do it. But what we're going to look at is a set of data that looks more like this. Now, in that case, does it look like a line would be a good fit for that data?
Not for us.
No. And you can kind of draw a line through it, but the point is, if you try to use that line to predict what's going to happen, the line in the long term is not going to do a good job. You want something that probably looks more like that. That's a curve. That's going to be a curve of best fit. So there's lots of kinds of curves. Is that a parabola? Maybe that would be a good one. Or is it cubic? We can calculate up to, I think, a 4th degree curve on the calculator. So we can do linear. That's degree 1. Quadratic curve would be degree 2, degree 3, and degree 4. If you want to try to find a polynomial that's higher than degree 4 that's going to fit that data, the graphing calculator with what's built into it can't do it. But you could probably download something to be able to do a degree 5. We're going to look at a special type of curve called a power law, okay, or a power curve, or a power function. And a power function is basically, you can think of it as a polynomial that's a single term. It's a single term. Y equals 3x squared. That would be a power law. Y equals negative 8x to the 5th. Generally, the A and the M they could be fractions or decimals. That's what we're going to try to find. And if we go to the calculator, on my calculator, probably if you're using mine, it'll be the same. Power regression is the option we're going to look at.
Okay, alright, is this all under stat?
This is all under stat, yep. And power regression it's not the only kind of curve, but it's the one we're going to do because it has something to do with logarithms. That's why we're going to do it. Before you use a power regression, you have to decide, is a power regression the type of curve I should even try? Right? Because the calculator can do lots of them. Why should I use this one? Well, using logarithms, you can figure out if this is the best one to try to do. I'm not going to go through that. So how do we determine if we should use a power model to fit a set of data? So you're going to be given a table of data like this. The first step is to take the ln, take the natural log of every single number in this table. So you're going to make a new table. The new table is going to have the natural log of every single number right here. So that's step one. Then what we're going to do is we're going to look at that new table. We're going to do one thing with that new table, and then we're going to forget about that new table. All we're going to do with that new table is take those points and graph them. If it looks like that new set of points are in a straight line, then that means a power model is the right thing to use. The closer they are to a straight line, the better. There's actually two ways to figure out if you should be using a power. The first way is take the ln of all your data and make a new table. The other way would be make a new piece of graph paper. And the graph paper would handle taking the log for you, the way the paper is drawn. So I'll show you that. I'm not going to do it on this type of paper right now. I want to do it the way I showed you. But there is another type of graph paper called log graph paper. And that looks something like that. So the spacing is not equal. The spacing is set up logarithmically. And if we used this graph paper, we could avoid this step that I just told you. But we're going to use regular graph paper. So we're going to have to do this step. Okay, I'll show you the other paper. Maybe. We'll see. It's not used. We don't use it very often. All right. So let's look back at our formula. Y equals ax to the m. There's two things that we need to find. The a and the m. And the way we're going to do it is we're just going to use the calculator to find those values for us. So let me rewrite this. Step 2. Use the graphing calculator to calculate, it's called power regression, PWR-REG. On my calculator, it's option A. I don't know, if you use a different calculator, it might not be option A.
How would you select option A?
You just go right up to it and then just hit enter.
Okay, there's like a shortcut like numbers.
Yeah, you could do alpha and then press math, and that would be A.
Interesting.
Yep. And then once you do a power regression, the calculator is going to give you two numbers, kind of like it did right here. Well, the last step is to take those two numbers and fill them into the formula and write your final answer. So step 3, sorry. Write the final answer in in the form y equals a times x to the m. I think those are the two letters the calculator uses. Well, we'll find out when we do one. Let me try to fit a power regression to that last problem. Okay, it uses a times x to the b. So they call it b, they don't call it m. If you use a different calculator, it might call it b. Might call it m. Might call it a different letter. It could be a little different.
How did you find out what it calls it?
I just went through and actually did it on my calculator, but we're gonna do it for the data set that I have right now. All right, so here's our data set. First, determine if a power model is appropriate, and if it is, then find it. So what's the first thing that I said to do with every number in that table?
To find the natural log.
Find the natural log. And I'm going to show you a quick way that you can do it all at once. Well, at least 2 steps rather than 8 steps. Because I don't want to type every one of those numbers in one at a time and find the natural log. So I'm going to put all these numbers in my table. And by putting them in the table, if it ends up that it looks linear, and I'm supposed to be doing a power model, then I'll already be ready to go because the numbers will already be in here. So you go to Stat, go to Edit, and I do all my x's first because that's when I hit Enter, that's how the calculator does it. And put in your y's. So 5, 31.2, 73.1, and 160.
How do we get to that screen?
Stat and then Edit. Stat is below delete. Now, I want to take the ln of every number in that table. Where did I put my x's? In which list? L1. So here's what you can do. You can type ln, and now I want to take the ln of L1. Every number in list 1. Press second 1. Close your parenthesis. And that's going to take the natural log of every number in list 1. It's not going to change list 1. It's just going to show me all the answers on the screen. So I want to write all these numbers down in a new table. ln x, ln y. Okay. And we're going to graph it. So, I mean, 1 decimal place is plenty. That's all you need. We're not going to be able to graph more precisely than that by hand anyway. So we've got 0. We've got 1.1. We've got 1.6. And about 2.1. Now I want to take the natural log of every number that was in the y values, and that was L2. So let's do natural log, second 2. All right, so we get 1.6. These two numbers should be the same in this problem, because they were the same. So 1.6. 3.4. I can't see the rest.
That should be
4.3 and 5.1. Now, the only thing we're going to use this table for, now we can throw this table away, is just to see if it looks like those numbers line up in a straight line. The more of a straight line they look like, the better the power model is going to be. Alright, let's try it. So this part, I'm just going to do by hand. Let's do it on the first piece. Okay, do I have any y values or x values that go beyond 5?
5.1.
That's it. We can deal with that. Alright, so let's copy and paste. That is not what I wanted to paste. Alright, I'll just do it like this. Okay, so my first point is 0, 1.6. So 0, 1.6. We've got 1.1, 3.4. So 1.1, 3.4. 1.6, 4.3. So 1.6, 4.3. Maybe about right there. It's looking pretty good. 2.1, 5.1. So just above 2, just above 5. So just above 2, just above 5. Maybe about right there. Do those points look like they're in a straight line? I'd say it looks like you're almost in a perfectly straight line. So that means a power model is appropriate for this table. We're done with this table in red now. We can get rid of that table in red. We don't need it for the rest of the problem. It was just to check if we should use a power model. Okay, so because we already put all the data in when we were doing the LNs, that's one step we can skip right now. The data's already there. So keep that data there. Go to Stat, Calc, and which option did I say to pick?
A.
Option A, which is a power regression. As long as you put your x's in L1 and your y's in L2, you don't have to change where it says the x's and the y's are. If you used L3 and L4, that's okay, but you need to tell the calculator that right now. Okay, we used L1 and L2, so we're good. Go to calculate. And that's what it gives us. We should round these answers appropriately. So what do you think A should be rounded to? 5. 5 times x. And what do you think my exponent should be? How about we do it as a fraction? Yeah. 1 2/3, which would be as an improper fraction? 5/3. That's probably what it is. I mean, when it repeats 6 or 7 decimal places in a row, we can assume that it probably should just keep repeating for that number. If we had more accuracy with the original data, we probably would have gotten an even more accurate answer for A and B. But they only gave us 1 decimal place in the data. So. All right, so that looks like it's the power model. Well, let's see. I already have the data typed in. What was my smallest x value?
0. No. Yes. No. 1.
1. So let's do 0. How about my biggest x value?
8.
8. So I think 10 is okay. How about my smallest y value? 5. So let's do 0. Biggest y value?
160.
All right, let's do 170. And I'm going to hit graph. My scatter plot is still on because I never shut it off from the first one. If yours isn't on, go to y equals, go up to plot 1, and hit enter, and it should look like there's a black box. Now, I want to type in that equation and see how good it is. If it goes right through those points on the screen, then it's a pretty good equation. If it doesn't, then we might have done something wrong. Yeah? Yeah. So let's type in 5x to the 5/5. What do you think? Does it look like it goes through the points pretty good?
Yeah.
It's not going to get much better. So it's just about perfect. In fact, there's something we could turn on the calculator, and it would tell us how perfect it is. There's a number that goes between like 0 and 1, and the closer it is to 1, that means it's like 100% fit. If it's closer to 0, that means it's like a 0%. So this one would probably be like 99%. It's like, it's just about perfect. And that's how you find a power regression. Now, when I did second, let's go back to stat. I did calculate. I did option A. There's something there I didn't really talk about. Well, it's not letting me. That's not the screen that's on the screen. Well, let's just look at it from here. The fourth thing down, it says store. See, it says store, and then it says REGEQ. It actually put this answer in the calculator somewhere. It saved it. So if I wanted to check how good of a fit it is, I don't actually have to go and type in y equals 5x to the 5/3. I could have just recalled it from where it's already saved. And let me show you how you can do that. It's storing it in a variable called regression equation. I'm going to clear that. And what button have we been using for pretty much everything today? All right, so if you go to stat, you might think, well, it might be able to find it there. But I'm looking for something that says regression equation. I don't see it. Calculate, REGEQ, I don't see it. And then under tests, that's all statistics stuff. We don't talk about any of this in this class. But there's nothing here that says REGEQ. Well, I told you that that's a variable where it's stored in. And there's a button on here for variables. That's where it is. If you press vars, you'll see, let me just check it first. Yeah, okay. So press vars. And we've been calculating statistics. So if you go to statistics, the calculator will give you all your statistics variables that are in the calculator.
Sorry, where did you go?
Vars and then option 5. Now, specifically, we calculated an equation. Well, the third option over on the top is for equations.
Oh, dang, that's supposed to say. I mean, well.
If you press enter right now, it's going to put that equation on the screen. That's exactly the equation we just had. So it tells me the exponent, it was that, what was it, like 1.6 repeating. And then the a value, I have to scroll to the left so you can see it. 4.99938. So it gives me what it calculated automatically. Now, I want to graph it, so I don't want to just put it in on the screen where I do arithmetic. I want to put it in on the y-equals screen. And it'll put that equation right in what I want for it. How do I get to it again?
The
Variables, yeah. 5. And then equation. And there's all kinds of variables that it saves. I'm interested in, well, I could probably get just the A or the B value if I really wanted it. It has those separate, but I want the whole thing. So I hit regression equation, and it puts it in automatically without me having to type. Now, that's not that bad to type, especially when you round it off. But some equations, especially if you had like a cubic, the formula might be like 3x squared minus 5x cubed plus 7x minus 10. It might be a lot to remember or try to type in. So if you do it the way I showed you, you don't have to remember what it is. It'll just copy and paste it automatically. And there's basically the same equation we just did. when we write our final answer, we are always going to round it appropriately. And the one you have on the test, it will come out to a somewhat nice number, like this. I would consider those nice numbers that you can round off. Any question on that? All right. So, told you we'd take a look at this piece of graph paper. Has anyone ever used log graph paper before? Might be something if you're in like engineering, you might use it. Other than that, it's not used a lot. So, first thing we had to do is we had to figure out if a power model was even the right thing to try. So we took the outline of everything, we made a new table, and it looked perfectly straight. That told us it was a good thing to do. But it took a little bit of time, especially if you didn't have a graphing calculator. You'd have to take the ln of every single number in the table by hand. Well, another way you can do it is instead of taking the ln of all your data and using the same type of graph paper you're used to, is keep your data the same and change your graph paper instead. And you can still see if it's linear or not. All right, so when you look at logarithmic graph paper, first of all, you notice that it's not spaced evenly. It's spaced at different intervals. And the spacing is set up so that when you graph on this type of paper, let me graph log. Let's just turn off my scatter plot and type in log of x. And I look at that. And this piece should keep coming down. Is this graph a straight line? No, not on that type of graph paper. Because this type of graph paper has equal distances between every tick mark. But if you graph a log function on this paper, it comes out straight. That's what logarithmic graph paper does. It takes anything that normally would look curved on regular graph paper, that's a log, and makes it look straight. So that's why if we plot the points from our original table on that graph paper, and these points come out straight, not these points. We don't have to do this if we change our graph paper to use different paper. If we use this, and it comes out straight, then we're good. What we have to look at is how is this numbered? Well, okay, so it starts with 1, and that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Now it goes by tens. That's 10. That's 20, 30, 40, 50, 60, 70, 80, 90, 100. And then it goes by hundreds. 200, 300, 400, 500, 600. So the scale isn't consistent. And it works the same up and down. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it goes 20, 30, 40, 50, 60. So the scaling is a little different than what we're used to. Now, I need to see how big of numbers do I have. My y's go up to 160. Okay. So what I'm going to do is, I probably should have started down here, which is fine. Can somebody tell me what was my first point in the original table? 1 comma? 1, 5? Yeah. Okay. So 1, 5. Let's start from here. So write 1, up 5. 1, 2, 3, 4, 5. Did I do that right? 1, 2, 3, 4, 5. I counted wrong. Okay, what was the next one? 331.2. So let's go 3. 1 here. 2, 3. Oh, messed that up too. Can't count apparently. 331.2. So 3, and then this would be 10, 20, 30. See, I'm not as familiar, so it's all I have to count. Almost like I'm learning how to graph for the first time. It's a little harder. All right, and let's just do one more. What was the next one?
573.1.
573.1. Okay, so 1, 2, 3, 4, 5. And then I go up to 73. So there's 10, 20, 30, 40, 50, 60, 70. Right about there. Does it look like those points are going to be in a straight line? Yeah. So because these points are in a straight line, it tells me that a power model is going to work well for the data. So there's two ways to do it. Keep your points the same, change your graph paper, or keep your graph paper the same and change all your points. Either way. I'm just not as familiar. I usually change my points to do the test because I'm not as familiar with logarithmic graph paper, and I usually don't have it on hand to do that. So, regular graph paper I have, and I can use the calculator. You can't do logarithmic graphing that I know of on this calculator.
Like with the logarithmic graph paper.
Yeah, I don't think you can. I don't think you can do that. If you can, I'm not sure how. So. Okay, so that's 5.5. Solving those equations algebraically, like about population growth, and then looking at power regression. Any questions on that? Okay. All right, so we didn't cover 301. That's going to be part of tomorrow. Let me double check. Yeah, I might have to change that a little because we didn't cover anything on the bottom. So. Let's see. So I want to do and don't worry about 35. Here we go. You know what? I just make it 43 to 48. That's simple. So that's the homework for tonight. 43 to 48. We'll take a look at that tomorrow. If you want to copy down the 301, you can. I may tweak that a little bit, but it's probably going to be pretty close to that for tomorrow. Okay, so just 293 for tonight.